So thank you. I'd like to thank the organizers for the invitation. It's always a pleasure lecturing at the Catholic Asian Winter School. This is actually my 4th time lecturing in this school, twice in Japan, and this is my 2nd time in Korea. And I'm looking forward to meeting and talking with the participants of the school in the coming days. So, unlike other lecturers, I have chosen a more conjectural topic for my lectures. Now, the word conjectures may give you the impression that what I'm going to say are all speculations. This is true to some extent, but as you will see, there are bases on which these conjectures were made. And we should also not forget that conjecturing is part of the scientific process in formulating the laws of physics. A long time ago, drawing lessons from the measured spectral lines of atomic transitions bore conjecture that angular momentum are quantized. Now, this was a rather bold move at that time because, as far as I understand, there was no theoretical reasoning behind. But the power of these conjectures is not only that it can explain the existing data at that time, but it also leads to new predictions that can be further tested by experiments. And of course, we know eventually his conjectures can be understood in the context of quantum mechanics. Nonetheless, it was a major stepping stone for its advance. Now, the Swampland conjectures that we will discuss in these lectures were made in a similar spirit. Now, unfortunately, we don't currently have a lot of experimental hints on what lies beyond the standard models. But we have lots of theoretical data. Now, you can think of the theoretical data that we have as our ways of understanding what kinds of universal features of UV completion of gravity should be. And so these universal features that we find from the limited theoretical understanding we have about quantum theory of gravity would be the basis on which these conjectures were made. Now, as you will see in the upcoming lectures, these conjectures, if true, could lead to rather interesting predictions in particle physics and in cosmology. For instance, in constraining models of inflation that give rise to a detectable level of gravitational waves, the physics of dark energy, and in the case of particle physics, the physics of axions, and possibly relating some beyond the standard model of physics with the observed cosmological constant. Now, this is far from a complete story, very different from the nature of the other lectures that were given in this school. It's still very much work in progress. Testing some of the conjectures that I would explain in these lectures and finding out what is the fundamental reason behind them, it's still a rather active research area. Now, the analog of quantum mechanics is still out there. We don't know what is the reason why this conjecture seems to work, but precisely because it's not understood, that makes this research program particularly exciting. Perhaps some of you can find out what exactly is the reason behind some of these conjecture properties of quantum gravity. Now, the motivation of this so-called Swampland program is to understand what to do with the seemingly large number of solutions in string theory, often known as the string landscape. The question is, has string theory become so rich that anything goes? Namely, any possible low-energy effective field theories can be realized as a solution of the theory. Or perhaps there is even a bigger swampland out there. And if so, where do we draw the lines? Where precisely are the boundaries of possibilities between theories that can be consistently coupled to quantum gravity and those that cannot be? Okay. Now, the term swampland has been used to refer to the space of quantum field theories, seemingly consistent quantum field theories, which are nonetheless not consistent when you start to couple the theory of gravity. Obviously, knowing where the boundaries of possibilities are, we can still make falsifiable predictions, even though the landscape may be vast. Now, the Swampland program, therefore, is about extracting possible universal predictions from string theory and to find out what are the rules that govern them. This is obviously a very tall order because the space of quantum field theories is huge. There are many, many possibilities. How do we know that, any given theory is within this vast number of possibilities can be embedded into a quantum theory of gravity. Moreover, what we can really measure experimentally are phenomena at energy scales that are much, much lower than the scale at which the fundamental theory of gravity is defined. So this is obviously a very challenging research program. Now, I can at least name several major challenges for this program. This is not to discourage you, but just to be honest with you that there are still a lot of unknowns. So a major challenge in understanding the scope of the landscape versus the swampland is that we don't currently have a complete definition of string theory. So all we have are just bits and pieces. We know certain fundamental degrees of freedom, such as strings. They're higher dimensional generalizations that we call branes. We know that there ought to be a lot of gauge fields and fluxes that couple to these objects. And we also know that there are lots of different possibilities for the extra-dimensional geometry. So these are the ingredients that we have. But how are we sure that we are not biased by our lampposts? So all we can say at the moment are things that we know, but there are a much bigger space of possibilities that could potentially be missed because our current technologies have not reached such possible realizations of string back here. Another challenge that you could immediately see is that there are different degrees of concreteness for what we call a string constructions, ranging from a fully explicit one, namely you specify what exactly is the internal geometry, you stabilize the moduli, you know what are the gauge and gravitational degrees of freedom of the theory, as well as the interactions between them, to something that one would call string-inspired model. Namely, there are ingredients that seems to be suggested by string theory, but you don't have a fully complete and explicit constructions based on the microphysics. Now, those who have worked on this subject would know that the closer you get to the string, to the explicit end of the spectrum, the less realistic the models become. Usually, the more explicit end of the spectrums are theories with a lot more supersymmetries to have more control. So it doesn't seem like this would give us anything close to the real world or any quantum theory coupled with gravity that could be of interest to us. Now, you could get more and more realistic models if you relax some of the assumptions and go to the more string-inspired end of the spectrum, but then the models are not fully stringy. Now, drawing the analogy with the Bohr quantization condition earlier, quite different from the time of Bohr, the spectrum of string theory solutions, unlike the atomic transition lines that guided Niels Bohr in postulating his quantization conditions, there are theoretical contaminations. There are features that may not be actually stringy, but just happen because when we try to look for string-inspired models, we don't have a fully explicit constructions. Nonetheless, we could still make progress by combining insights from various fronts. We would try to get as much insight as possible from various possible hints. Now, the string constructions, even though they are rather limited, and the ones that are known to us are rather limited, they can serve as our theoretical data as well as our testing ground for testing various conjecture properties of quantum gravity. And you see that it would come into play in some of the lectures in the coming days. Another important hint that one could get is by studying general properties of quantum gravity. Some general quantum gravity arguments, especially motivated by black hole physics, also give us another handle on what are the universal features of quantum gravity. And as you will see, string theory oftentimes also teaches new lessons about microphysics. And this microphysics that we learn from string theory may also lend further support to these conjecture properties of quantum gravity. So we will try to combine insights from various different fronts in formulating a conjecture and in testing them. Now, before we discuss this different swampland conjectures, evidences for them, and the applications, let me briefly say a few words about the swampland program. Now, it is oftentimes said by the critics that the swampland conjectures are just a bunch of wild speculations. This is far from the truth. What we have is an intricate web of proposed consistency conditions for quantum gravity. Now, the reason why we have so many different conjectures about quantum gravity is that the rules of quantum gravity are not quite well understood. And we expect the number of conjectures to reduce when we understand the principle behind. Now, I will come back to this slide at the end of my 4 lectures, because some of these terminologies here may not mean anything to you yet. But the point I want to make here is that this intricate web of conjectures about quantum gravity shows how quantum gravity has put us in a straitjacket. If these conjectures were just random guesses, there's no reason why they have to fit into this intricate web. This also gives us confidence that if we understand very well, or perhaps prove one of these conjectures, we may find out what is the underlying reasons for these various different statements about quantum gravity. Okay? Now, before we talk about some of the new conjectures about quantum gravity, let us start with a conjecture that predates the discussions that happened in the past 10, 15 years. And that is the conjecture that global symmetries do not exist in quantum gravity. Now, this is oftentimes not discussed in the context of the Swampland, but you can think of this statement about quantum gravity as being a way to distinguish consistent theories with those that are not consistent. So what was the statement? Well, the statement is that in the consistent quantum theory of gravity, you don't find exact global symmetries. And there are many ways to motivate this conjecture, and with different level of concreteness. Okay? The simplest ways to motivate this conjecture is to consider black holes. So you can motivate it by thinking about this thought experiment. Now, the Hawking radiation of a black hole is insensitive to the global charge that it carries. So if you have black holes with different global charge, they will Hawking radiate. And eventually, this will lead us with infinitely many indistinguishable states within a finite mass range. And this could violate the entropy bound. And indeed, all symmetries in string theory, as far as we know, are gauge symmetries. Now, this is just a heuristic argument. A better argument can be made if you are looking into particularly perturbative formulations of string theory. In fact, that was a proof back in the 80s by Banks and Dixon. The argument is basically that whenever you find a global symmetry current, you can, at the same time, construct a vertex operator for gauge bosons. So that means that the symmetry is gauged. Now, this conjecture about quantum gravity has recently been revisited in the light of ADS-CFT. And even though this argument is only applicable to quantum gravitational theories in the anti-de Sitter space, the arguments have extended the previous proof of the perturbative string theory case, by including also discrete symmetries. So the earlier argument only applies to continuous symmetries that has to be gauged, but recently, by applying holography, you can show that even discrete global symmetries are not realized in quantum gravity. Now, this is just a teaser. We would come back to this later on, but let me just mention that there are many phenomenological ramifications of these conjectures. If we can actually prove it, then it would be, of course, a much stronger statement that we can make. So one possible phenomenological applications you can think about is to use it to show that if the dark matter particles carry a tiny electric charge, there must be necessarily a new massless gauge boson. Okay? Now, the argument is very simple. It can be made as follows. We know that the dark matter particles have to interact very weakly with the standard model, but it has not excluded the possibility that it carries a tiny electric charge, as long as the charge is small enough. And in fact, phenomenologists have considered models of that type, where the dark matter particles carry a tiny electric charge. This number epsilon here could be extremely small. As long as they are small enough, they are not ruled out by current experimental bounds. Okay. Now, let's see what happens if you have such a model with a tiny electric charge. How is that compatible? How is that incompatible with the conjecture of no global symmetries? Well, let's say if your dark matter particles carry a charge that is not quantized with respect to the electric charge, one thing which you immediately realize is that you can construct neutral operators purely from the standard model fields or purely from the dark matter fields. And as a result, you find that there is a global symmetry that acts only on the dark matter sector without touching anything of the standard model sector. But as we argue, a global symmetry of this type is not allowed unless the symmetry is gauged. So this is essentially the argument why if you have a dark matter particles that carry a tiny electric charge, tiny irrational electric charge, there's necessarily a new massless gauge bosons. Now, if you are a bit more precise, you'll find that strictly speaking, this argument does not exclude the possibility that the dark sector carry a tiny but rational electric charge. There are actually names for that. They are known as F-chams, fractionally charged massive particles. However, as I would now argue, this scenario is highly contrived. It would require severe fine-tuning. Now, to get a small rational charge would require a very large integer. It's a ratio of integers, so the integers have to be very large, which can be realized if you have, say, large quantized fluxes. In string theory, there are large integers that you could imagine. For instance, the fluxes in the internal space, they're quantized, they could take very large values. However, these quantized fluxes are limited by Gauss' law constraints, and so there's a bound on how big these integers can be. And while we cannot rule out this possibility that the dark matter carries a tiny rational charge, a more natural solution is for the symmetry to be gauged, in which case there's a new massless gauge boson. So that completes the argument. Now, then what is the weak gravity conjecture? This is one of the conjectures that we will spend quite a bit of time explaining and trying to find arguments in support of the conjecture and seeing the applications of it in constraining models of inflation, for instance. Now, the connections between the weak gravity conjecture and the conjecture that there are no global symmetries in string theory is the fact that global symmetries can be thought of as gauge symmetries with a very small gauge coupling, with vanishing gauge coupling. So it's natural to suspect that problems would arise when the coupling constant becomes sufficiently weak. The question is, when do things go wrong and how? Okay. So the weak gravity conjecture is an attempt to formalize this suspicion that something goes wrong when the coupling constant becomes too weak by postulating that for every long-range force, there must exist a state whose charge to mass ratio is bigger than 1, or more precisely, the charge to mass ratio of an extremal black hole. And an extremal black hole is one which has 0 Hawking temperature. And in this weak gravity bound, you see that the charge that appears here is the quantized charge multiplied by the gauge coupling. So there is a limit on how weak the coupling can be without violating the weak gravity bound. Okay. Now, one of the supporting evidences for the weak gravity conjecture is that it seems to hold in all known string theory constructions, but this is not a very strong argument. It could just be that we are not creative enough to find new string theory models that violate this bound. So the question is, why would this conjecture hold true? Now, there's a heuristic argument made in the original weak gravity paper. The argument is basically the following. Imagine that you have a theory that violates the weak gravity conjecture, namely that all the particles in the theory have a charge smaller than its mass in appropriate Planck units. If so, then it's very easy to see that the gravitational attractions between these particles are stronger than the gauge repulsion, so they can form bound states. Now, these bound states, you can, with a moment of thought, you can convince yourself that this is not only 1 or 2 bound states, but an infinitely many bound states. And these bound states cannot lose the charge and do not Hawking radiate once they reach the extremal limit. So we end up having, again, infinitely many stable states. Now, what the weak gravity conjecture does is to postulate that there should not be a large number of exactly stable objects, if not because of a symmetry. So to avoid these situations from happening, you can postulate the existence of a state whose charge to mass ratio is bigger than 1, so this process would not go on forever. At some point, this chain will stop. And you don't find, there's a channel for these bound states to decay, and so there's not going to be infinitely many bound states as a result. Now, this is sometimes known as the mild form of the weak gravity conjecture. We will make that distinction more clear in the subsequent lectures. There are different versions of the conjectures. This is the mildest form. It only requires a state satisfying this inequality, but with no additional assumption on what that state might be. It doesn't have to be the lightest states in the spectrum, nor do we need more than one state satisfying this inequality. Now, if you think for a moment, you realize that this argument is a lot weaker than the no global symmetry conjecture. Even though we have infinitely many stable states, we don't run into the same problems with remnants. Even though we have infinitely many stable states, within a finite mass range, there's only a finite number of such states. And the argument made earlier is if you have infinitely many stable states within a finite mass range, let's say with a mass below the Planck scale, you would run into problems with remnants. One way to see the problem is that if you consider loops of particles running in loops of particles that correct Newton constant, if you have infinitely many stable states within the finite mass range, they could renormalize the Newton constant to 0 and turn off gravity. Here, you cannot make that argument because these infinitely many stable states are all spread out in terms of the masses over an infinite mass range. So that's the reason why it's not so clear at this moment why the weak gravity conjecture should hold, even though it seems to be satisfied for all the known string theory constructions. So let me now turn to some evidences for the weak gravity conjecture. Up to this point, several independent lines of arguments have given support to the weak gravity conjecture, and we will discuss this in more details in the coming lectures. Just to mention a few arguments, the weak gravity conjecture implies through holography a bound on the conformal dimensions of operators in a dual CFT, which has been verified in some cases. And there's also an intriguing relations between the weak gravity conjecture and the cosmic censorship conjecture. And we would discuss in more details how infrared consistency conditions, such as unitarity and causality, can provide support for the weak gravity statement that I made earlier. Now, this is also a place to mention that other than the mild form of the weak gravity conjecture that I mentioned here, there are stronger versions of the conjecture. Stronger means that you would either put additional requirement on the states that satisfy the conjecture. For instance, the state has to be either the lightest states in the spectrum, or there ought to be an infinitely many charged states that satisfy the inequality. And we would turn to some evidence for the stronger versions of the weak gravity conjecture in the lecture tomorrow. And some of these stronger versions of the weak gravity conjecture requires infinitely many charged states. For instance, something that we call sublattice weak gravity conjecture or tower weak gravity conjecture. That means that the conjecture has to be satisfied by infinitely many charged states in a charged lattice. And these stronger versions of the weak gravity conjecture is motivated by internal consistencies. If you embed the gravitational theories in string theory, this seems to follow from criteria such as modular invariance. And you could also see that a stronger version is necessary, as we will do so later on today. Consistencies among a point Kaluza-Klein reduction or compatibility with T-duality would also give evidence that not only do we need to find a state that satisfies the conjecture, you need to find infinitely many stable charge, infinitely many charged states. Now, although I said I would describe this evidence for the weak gravity conjecture in more detail later on in the lectures, But as a teaser, let me just briefly mention what the weak gravity conjecture can say about properties of conformal field theory through holography. Okay? Now, the weak gravity conjecture states that in gravitational theories, there must exist a state whose charge to mass ratio is bounded from below. When you apply the weak gravity conjecture to gravitational theories, this implies through holography that there must exist an operator whose conformal dimension is bounded from above. Okay? Now, this duality can be applied to, in principle, to any dimensions, but because of the enhanced symmetry algebra of the two-dimensional CFT, you can find very strong constraints on the spectrum of operators. And one can make use of modular invariance and charge quantization to conclude that there is an automorphism of the current algebra known as the spectral flow. And so the spectral flow mapped the spectrum related by these relations over here. Now, you could start with a state that you know must exist, namely the vacuum, and applying the spectral flow to the vacuum would imply a bound on the conformal dimensions of the operators for a given charge. So this is reminiscent of the weak gravity bound, which constrains the charge to mass ratio of particles, but in the CFT language. Now, strictly speaking, this is a bound not only for a given charge, but the fact that we have a spectral flow naturally splits the spectrum into different sectors. In fact, K sectors, where K is the level of the current algebra. And so what you show here is not that the conformal dimension is bounded for any given charge, but you only show it for a sublattice of the full charge lattice. And this suggests what we call the sublattice weak gravity conjecture, namely for any sublattice of the charge lattice, there is a bound on the conformal dimension of the operators. Now, this was an argument made based on spectral flow. Recently, there was an interesting work done by the Kias group. They find using the modular bootstrap approach a slightly weaker bound, but it's compatible with what I have written over here. And so given that this bound was derived from a slightly different approach, it gives non-trivial evidence for the conjecture, sublattice weak gravity conjecture. So the reason why I mentioned the sublattice weak gravity conjecture right away is that this is oftentimes discussed along with the completeness conjecture, even though they are not the same thing. Okay? So what does the completeness conjecture say? Well, the completeness conjecture states that in a consistent theory of quantum gravity, all the charge states that are allowed by Dirac quantization should be populated. Okay? Now again, there's no proof of the completeness conjecture, but one can make some heuristic arguments. One heuristic argument that one could make is to think in terms of charged black holes. Now, the entropy of a black hole has an interpretation as in terms of black hole microstates. And if the black hole is charged, so are the corresponding microstates. So since the black holes can carry arbitrary charge, there must be, so all the charge states must be allowed in the spectrum. Okay? Now, this is a rather heuristic argument. A slightly less heuristic argument can be made by requiring factorizations of correlators in ADS-CFT. Okay. Now, notice that the completeness conjecture that I stated over here makes no references to the mass of the charged states. There's no need for the states to be accessible in the low energy effective field theory, nor do we know how to bound the masses of these states given their charge. So that's the difference between the lattice or sublattice weak gravity conjecture with the completeness conjecture. The completeness conjecture just requires the existence of such a state with a given charge. Doesn't mean that the masses are bound, but the sublattice weak gravity conjecture is a slightly stronger statement. It requires the corresponding charge states to have a mass bounded by the weak gravity relations. So let me briefly mention some generalizations of the weak gravity conjecture that would be useful later on. Okay, but before I do that, let me stop here to see if there are any questions. Yes?
So the black hole solutions are described reliable when charges are macroscopic, and how do you know that the all allowed charges are populated even for order 1 charges?
So good. So that's why I mean by heuristic argument. We can only do it for very large black holes. If they are not macroscopic black holes, I don't know. Mm-hmm. Right, but the question is whether the small charge, the small. Yeah. Yes.
I have a couple of questions actually. So first of all, like the space of theories you showed in this Swampland and this thing, the theories by like each point in that space. Do you mean that theories like, I mean there are 2 points, they are RG connected, or like these are like different?
Sorry, can you say it?
So like the space of theories, they are like, are you considering the theories which are connected by the renormalization group flow?
So maybe you can speak again more slowly. I had a hard time.
So what I'm saying is like in the space of theories, are you, I mean in the whole space, by whole space, are you mean that, do you mean that like you are also considering the theories which are like connected by renormalization?
Well, so, yeah. Well, we don't know, you mean the completeness conjecture. We don't know the mass of these states. It could be very massive.
Okay. So another thing is like in the, like, this weak gravity conjecture, as I'm understanding, like, is that, that conjecture, so that is a statement about the UV complete theory or some effective field theory. Like, I mean, it may be that true that like it is in the original, like at the like very high scale, the thing is satisfied, but like in the scale of experimentation, it may not be.
So originally it was formulated for theories of the infrared because it was thought to be motivated by black hole physics. So the infrared scale would be the black hole scale. However, as you will see in the subsequent lectures, the line between infrared and UV will become more blurry when we especially talk about the lattice weak gravity conjecture, when there are a whole bunch of states populated with very large masses.
Okay. One more question. So when you say that like no global symmetries, so like for example, we know that like for gauge theories there is this asymptotic symmetries. So do you say that these, I mean, you don't consider them as global symmetries? Like for example, like in gauge theory there is this like large gauge transformation symmetries. Do you don't consider them as a global symmetry?
So yeah, so let me just state what I just described. So the statement is, whenever you find a global symmetries, there's a gauge boson. So I think that's, yeah, so you are referring to the soft theorem type.
Like a large gauge transformation symmetries. Kind of.
That is a more subtle case. Maybe we could discuss it more during the Q&A.
I have a question.
Yeah.
Yeah. So the weak, you derived a relation regarding the dimension of the CFT operators from weak gravity conjecture, right? Mm-hmm. So in the expression, if I recall, the right-hand side was I mean, there was no explicit reference to the M parameter that appeared in your weak gravity conjecture. Mm-hmm. So I mean, it certainly has to fit in somewhere, because otherwise it's conceivable that you can tweak this M parameter and violate the bound you have obtained, the upper bound you have obtained on the deltas. Yeah, this relation. So this M has to feature in somewhere, I guess.
What is the N parameter?
The M you have in the other equation. I mean, the weak gravity conjecture.
So the small mass becomes the conformal dimensions through holography.
Oh, okay.
Right, so this is, the form of this conjecture is basically bounding the charge to mass ratio of particles.
Okay.
Translated to the CFT language.
Okay. Thank you.
All right, so let me now turn to some generalizations of the weak gravity conjecture that we will use in the subsequent lectures. The simplest generalization is to write down the weak gravity conjecture for more than one U1s, for multiple U1s. Let's start with 2. So what would be the weak gravity conjecture for 2 U1s, say? Okay. Now, if the weak gravity conjecture is motivated by black hole decay, if you have a theory with 2 U1 gauge fields, there must be at least 2 charged particles for the black hole to decay. Okay. So the black hole can carry a charge under either one of the U1s. So there must be at least 2 charged particles for the black hole to decay. And as suggested by the single U1 case, it's useful to think of the charge to mass ratio of particles, but for a higher dimensional case, it would be more appropriate to think in terms of the charge to mass vectors. So that's why it's a 2-dimensional space. Now, right. Now, naively, it seems like we only need to find a state. So in this picture, the extremal black hole lies on a sphere with a radius that I have conveniently normalized to 1. So the points on the circle, on the spheres, are black holes that are extremal. And all the charged black holes lie within this extremal ball. And naively, it appears that we only need to find one state, each with a charge to mass ratio bigger than 1 in one of the charge directions, and then we are done. But this is not true because a black hole with charge in a direction somewhere not exactly in the diagonal would not be able to decay if you were only able to find a charge to mass ratio bigger than 1 in each of the charge directions. Okay. So you need to find states with a charge to mass ratio bigger than 1 in order for these black holes to decay, for this black hole with arbitrary charge to decay. And a more precise statement is that the convex Howard generated by the charge to mass vectors should be big enough to contain the extremal ball. So if you can find states with charge to mass vectors that are big enough to generate this polygon that is big enough to contain the ball where the extremal black holes lies, then all these black holes can decay. So the weak gravity conjecture becomes the conditions on the convex Howard generated by the charge to mass vectors. And this charge to mass vectors do not have to be orthogonal, as in these examples. As long as they are big, and as long as the convex Howard is big enough to contain the extremal ball, they would satisfy the weak gravity conjecture. So the weak gravity conjecture up to this point was stated for a one-form gauge field. But what the weak gravity conjecture is about is the existence of super extremal objects. So certainly we have such super extremal objects in the case of a one-form field, but there should be analogs of this weak gravity statements for p-form gauge field as well. So we would like to generalize the weak gravity conjecture to arbitrary p-forms, as you will see why this is useful in the subsequent lectures. To be slightly more general, instead of considering just the gauge field and gravity, instead of just considering a p-form gauge field with gravity, we would consider also an additional scalar that we call the dilaton. This dilaton couples to the gauge field in this particular manner. And the reason for this, for including this extra scalar, is because this kind of couplings appears very often in string theory and also in Kaluza-Klein reductions. So by considering charged black p-brane solutions in this p-form gauge field coupled with gravity and dilaton system, we are led to this inequality. So a super extremal p-brane would satisfy this inequality, where T is the tension of the brane and E is the charge of the brane. So this is a direct generalization of the charge to mass ratio of particles in the case of a one form, but you can generalize it to a p form as well. Now, strictly speaking, this extremality bound is only valid for p in between 1 and d minus 3. But it's interesting to examine the behavior of these super extremal conditions for arbitrary p if we naively extrapolate it. Now, let's assume for the moment that there are no dilettants. So we can set this coupling alpha to 0. You see that the extremality bound becomes degenerate for p equals to 0 and p equals to d minus 2. So these are the two extreme cases that are supposed to be outside the regime of validity, but let's assume that we can apply this formula and see what happens. Now, these two cases are clearly special. P equals to 0, the zero-form gauge field, the zero-form gauge field is an axion, and the corresponding charged objects that couple to it are instantons rather than charged particles. And instantons lack time evolution, so clearly it is very different from the other p-brane cases that are covered by this formula. Now, p equals to d minus 2 in 10 dimensions corresponds to 7 branes. This object leads to a deficit angle, and for sufficiently large tension, these objects would have such a large back reactions that it would destroy the space completely. So it's not surprising that there's no precise analog of the black hole extremality bound for these two special choices of p. Okay? Nonetheless, we will discuss the interesting case for p equals to 0 in lecture 3. And the gauge field in this case are the axions, and the corresponding charged objects are the instantons. And so we would discuss this special case because it would be interesting for applications of the weak gravity conjectures to inflation. And we will see that the axions that descends from string theory naturally has a non-trivial coupling with the dilettante, and this allows us to define the notion of an extreme mode instantons. In the case where the dilettante coupling is suppressed, there's no well-defined way of defining what we mean by an extreme mode instanton, but there is such a notion when this dilettante coupling is taken into account. Okay, now an interesting question is whether this weak gravity conjecture statement for P form is stable against dimensional reduction. Okay? So to address this question, we can compactify the theory on a circle. So you go from a d-dimensional theory to one dimension less. And so this would introduce for us an extra scalar, the radion, whose vacuum expectation value controls the size of the circle. Okay? Not only do you have an extra scalar that we call lambda here, it would also affect the dilettante coupling to the gauge field. And how this is modified, how this coupling to the gauge field, p-form gauge field is modified, depends on whether you are reducing on a circle that is along the brane or orthogonal to the brane. But it's a very simple exercise to work out what are the corresponding modifications. And you can see that from the structure of the dimensional reduced action, that only a linear combination of the dilettante and the axion coupled to the p-form field strength. The orthogonal directions is decoupled. Okay? Now, the one that couples to the field strength when you canonically normalize, it has a coupling that we call alpha. Okay? Now, it's a very simple exercise, and I leave it to you to show that the extremality conditions is stable against dimensional reduction. So a p-brane that satisfies the weak gravity conjecture, when you reduce it on a circle, no matter whether you're reducing along the brane or orthogonal to the brane, the condition is still satisfied. Okay? So that means that if the weak gravity conjecture is satisfied in the UV, in the infrared, below the scale of the KK scale, the weak gravity conjecture is still satisfied. Moreover, if the dilettante or the radion acquire a mass, if there's some mechanism to stabilize this moduli and they pick up a mass, the weak gravity conjecture only becomes monotonically weaker in the infrared because you can effectively set the dilettante coupling alpha to 0, and this condition becomes easier and easier to satisfy in the infrared. Does that mean that the weak gravity conjecture always becomes weaker, or at least stays the same in the infrared? Okay. This is not always the case, because remember, other than reducing the action to lower dimensions, you also, at the same time, could generate a new U1 gauge field. This U1 gauge field comes from Kaluza-Klein reduction. And this KK photons descends from the off-diagonal component of the metric. So it comes for free that when you reduce the theory, gravitational theory, to one dimension less, there's going to be an additional U1 gauge field, the KK gauge fields. And so you can read off the gauge coupling of this U1 gauge field that comes from dimensional reduction, as well as its coupling to the radion from the dimensional reduced action. Again, this is a very simple exercise of dimensional reduction. You can repeat it yourself. And the point I want to make here is that the Kaluza-Klein modes of this U1 gauge fields, of this KK photons, saturates the weak gravity bound. Now, there's no surprise here because the KK modes are the BPS states. So they satisfy the weak gravity conjecture marginally. Now, what is interesting is when you consider black holes with charge when you consider black holes that are charged under both this KK-U1 and an additional U1. This additional U1 does not have to come from Kaluza-Klein reduction. It can be just some other U1s in the theories. You find that the weak gravity conjecture is not necessarily satisfied in the infrared. And the reason is that the Kaluza-Klein modes only populate a finite density of points in the charge to mass space. So if you were to denote the particles that are charged under the KK-U1 and these other U1s on this two-dimensional space, the KK modes only populate a finite number of points. And you could see that when the radius of the compactified circle becomes too small, there would be points that there would be points on the extremal ball that lies outside the convex hull. So the weak gravity conjecture becomes violated when the radius of the compactified circle becomes too small. Okay? Now, one way to fix the problem is to impose a stronger conjecture, stronger than just existence of one state or for the black holes to decay. And a stronger version of the conjecture known as the lattice weak gravity conjecture has been proposed precisely because of this argument. So the lattice weak gravity conjecture states that for every charge Q on the charge lattice, there must exist a state whose charge to mass ratio is as large as a large semi-classical non-rotating extremal black hole with a charge that is aligned with this charge Q. Okay? So this is a stronger condition than the mild form that I mentioned before, because not only do we require the existence of a state that satisfies the inequality, you need that inequality to be satisfied for every point in the charge lattice. So these stronger versions of the weak gravity conjecture implies the convex Hall conditions that I mentioned before. Moreover, it is stable against toroidal compactification. So if it is satisfied, if the stronger versions, namely all the charge lattice, all the points on the charge lattice satisfy the weak gravity conjecture, when you reduce it on a torus, this conjecture is still true. However, these stronger versions of the weak gravity conjecture turn out to be false. You can come up with some counterexamples. The examples are not particularly pretty, but you can come up with compactifications in which you will find that some of the points in the charge lattice do not satisfy this inequality. So it's not always true. Rather, what seems to survive scrutiny is a weaker form of this conjecture. It's sort of somewhere in between. Instead of requiring the conjecture to be satisfied by every point in the charge lattice, you only require the conjecture to be satisfied by a sublattice of the charge space. Now, this is not something that you randomly pull out of your hat. There are some reasons to expect that the sublattice weak gravity conjecture should hold. One argument that I presented earlier was through holography. Okay? So through holography, you can argue that, in fact, this is an argument that I gave earlier. Using spectral flow, you can argue that the conformal dimensions of operators is bounded for a sublattice of the charge space. The sublattice here is defined by the level of the current algebra. So if you have a level K current algebra, the index of the sublattice is K. So So we have seen earlier an argument for this strong but not so strong versions of the weak gravity conjecture through holography. And in particular, the index of the sublattice is defined by the level of the current algebra. Now, there's even a more direct argument one can make, and this was made in this paper at around the same time. The argument is that if you are limiting yourself not to general string vacuum, but only to perturbative string theory, you could use arguments based on spectral flow on the world sheets. So again, you can prove a bound similar to the sublattice weak gravity conjecture by using spectral flow on the CFT, but this CFT is not the one that is the holographic duo of ADS3. Rather, it is the world sheet described. It is the CFT that describes the world sheet of perturbative string theory. You can show that by looking at the partition function of string theory. Using the spectral flow, you can argue the existence of such a state. Now, we don't know yet whether this sublattice weak gravity conjecture holds very generally. We only know that it works for perturbative string theory, and we also have seen that it works for holography in relating ADS3 with two-dimensional CFT. But there have been evidence for a somewhat weaker form of this sublattice weak gravity conjecture that we call the tower weak gravity conjecture. And we see that the requirements of infinitely many charged states satisfying the inequality also seem to follow from more basic arguments such as unitarity and causality. So again, from basic infrared consistency conditions, you seem to be finding evidence that there are infinitely many charged states satisfying an inequality that looks like the weak gravity conjecture, although this time the infinitely many charged states does not even have to fall within a sublattice of a charged lattice. It just has to be an infinite tower of states. Okay, so up to this point, what I have discussed are Swampland conjectures that are motivated in one way or the other by black hole physics. So the no global symmetry conjecture, the weak gravity conjecture, and various stronger versions of that were motivated in one way or the other by demanding consistencies with what we know about black hole physics. But there are Swampland conjectures that seem naively unrelated to black holes at all, and we will discuss some of them. Okay. One of these conjectures is known as the Swampland distance conjecture. So the Swampland distance conjecture is motivated by the observation that in theories with gravity, there seems to be a maximum field range beyond which a given effective field theory breaks down. Okay. So this is the case as we traverse along the string theory moduli space. Whether it is the string coupling or some geometrical moduli, we find that new states would emerge as we vary over a large field distance. Okay? So whether you are starting from type 2A, type 2B, or heterotic string, as you vary the moduli over a large enough field range, you'll find that the degrees of freedom seems to have changed. And the new states that emerge when you traverse over a large distance in field space would invalidate the EFT that you start with. The beginning EFT has certain low energy degrees of freedom, but you are missing the degrees of freedom that become slight. If you don't include them, the effective field theory would break down. And the Swampland distance conjecture is motivated by this observation that as you go to large enough distance in field space, you will find that there are some new states that become slight. And this new states, it would invalidate the EFT that you begin with. And in the case of string theory, we know what happened. You are just going to a different phase of M theory, where a different description in terms of different degrees of freedom becomes more appropriate. Doesn't mean that you cannot go further in field space. There's no fundamental limit on how far you can go, but there's a limit on how far the effective field theory that you start with in describing the physics will become invalid. So the Swampland distance conjecture is a way to formalize this suspicion, this observation. So for every point, so for every given point in field space, let's call it this P naught. This is the point that you start with in field space. There exists another point, P1, that is arbitrarily far away. That's essentially saying that the moduli space is non-compact. So as the shortest geodesic between these 2 points diverges, you find that a tower of states becomes exponentially light in the canonically normalized fields. So you find that not only do you have one additional light degrees of freedom, you find that there are infinitely many light degrees of freedom, and the masses scale exponentially. It drops exponentially with the distance that you travel. Okay. So the effective field theory would break down beyond a critical field range that I call lambda here. Okay. Now, subsequently, it was argued that the critical distance beyond which the effective field theory breaks down is always of order 1. This is the so-called Swampland, refined Swampland conjecture, and we'll have more to say about that in the third and the fourth lecture. Okay? So at the moment, you can just take this as an asymptotic statement. When you go to sufficiently large distance in field space, at some point, you will find that there's a tower of states that becomes exponentially light. When does this behavior start to kick in? It's a matter that we will discuss more in detail in the subsequent lectures. Now, to discuss this criteria in more detail, it's useful to clarify what we mean by the moduli space metric. Okay. So the effective field theory of a string compactification typically comes with many scalar fields whose expectation values describe the geometry of the compact manifold. For example, it describes the size or the shape of some compact internal cycles. And so the moduli space is the algebraic variety parameterized by the scalar field VAF. And now, if you write down the kinetic term for these scalar fields, they typically take these forms, where Gij here is the field space metric or the moduli space metric. And this is the metric that we will use to compute distances in the moduli space. Okay? So previously, when we say that the geodesic distance diverges, we are using this moduli space metric to compute distances in field space. Now, it turns out, in known examples of compactifying string theory, the moduli space is non-compact. And a simple way to see it is to look at some examples. So for example, you can consider the moduli space of type 2B string theory in 10 dimensions before you compactify. There's only one modulus, which is the axial dilaton, which is a combination of the string coupling and the Ramon zero form. And the field space metric looks like this. Now, the moduli space here is the complex plane modulo the actions of SL2C. And so you could ask, what would be the distances between 2 points in the moduli space? And so take a point in the moduli space to be, say, tau naught. This is a given point in the moduli space. You can see that for every given point in the moduli space, there is another point tau, which is arbitrarily far away when you go to sufficiently large enough distances. So when you fix a point in the moduli space tau naught, let's consider another point tau. When the imaginary part of tau goes to plus infinity, the geodesic distance indeed, you find, using this metric, you find that indeed the geodesic distance diverges logarithmically. Okay? So what that tells us is that as you go to the boundary of the moduli space, when you go to tau, the imaginary of tau goes to plus infinity, you are at the boundary of the moduli space, there should be a lot of like states that appear. And in this case, the like stringy states are the D-branes. The D-branes have masses that goes like 1 over the string coupling. As you go to the boundary of the moduli space, when the coupling goes to infinity, the masses of these D-branes becomes light. And these are the states that you need to include, without which your effective field theory would break down. And more generally, when you go to infinities, you are going to a singularity in the moduli space, where generically you expect new massless degrees of freedom would emerge. Okay? This is a point that we will make use of in the last lecture when we consider the de Sitter conjecture. Okay? Now, an important point I should mention here is that the new degrees of freedom that emerge at the boundary of the moduli space do not need to be massless particles. They just have to be light. There should be some light states as you go to the boundary. They don't have to be massless particles. They could be tensionless strings, or they could be tensionless branes. So to see this feature, we can consider another simple example. So compactifying a gravitational theory on the circle, okay, with a radius r, the kinetic term for the modulus, in this case the radion, take this non-canonical form. So this is the field space metric we can use to compute distances. And you can show that given any point in the moduli space with a value of the radius equals to r naught, you can always find another point with sufficiently large r that are arbitrarily far away. So this is because the field space metric, the field space distance diverges as you take the radius r to infinity. Okay? In the large radius limit, the field space distance diverges. This is just a statement that the moduli space is non-compact. And as you go to infinite distances in the moduli space, you find that indeed there's a tower of states that becomes light. Now, the masses of this Kaluza-Klein states that becomes light goes like 1 over the radius. It doesn't look like it's exponentially light, but it is exponentially light in the canonically normalized variable. Okay? So indeed, you find that a tower of states becomes exponentially light as you go to infinite distances in field space. But more than that, the Swampland distance conjecture also implies a much more remarkable statement, that in any consistent quantum theory of gravity, there must be extended objects in its spectrum. Now, these extended objects can be strings and could be branes. They just have to behave somewhat differently from point particles. They have to have an extent. So to see why this statement is true, you can consider going to the opposite limit in field space. Instead of going to infinite radius, you can consider the opposite limit. The field space distance, again, diverges logarithmically. And when you go to the small radius limit, when you send radius goes to 0. But what are these new degrees of freedom that becomes exponentially light as you go to this boundary of the moduli space? Well, this cannot be the particles. All the particles in the spectrum are the KK modes. And so they should become massive instead of massless as you go to the small radius limit. So they should not be the one that becomes exponentially light as you go to the boundary of the moduli space. And the only way to get this light states is to have extended objects that could wrap around the circle. In this case, the only compact directions that we have. And so what the Swampland distance conjecture says is that if it is true, anytime when you go to an infinite distance in field space, you see a new tower of states that becomes exponentially light, there must be some extended objects that give rise to this light degrees of freedom. And so this light degrees of freedom can come from strings wrapping around a circle that would become light particles as you string the circle to 0. These are the winding modes, the opposite of the Kaluza-Klein modes. They become massless in the small radius limit rather than in the decompactified limit. But more generally, the Swampland distance conjecture just says that there should be some objects that becomes light. They don't have to be particles. They could be extended objects. For example, if you have M2 branes wrapping around the circle, it would give rise to light strings in this limit. Okay? So the Swampland distance conjecture is nothing really surprising, again, based on what we know about string theory. When you go to the boundary of the moduli space, there ought to be a lot of like states, and this like state should have a mass that goes exponentially with the distance. And we identify what they are in several examples. We have identified it in the case of the axial dilaton. In this case, the like degrees of freedom are the B branes, whose masses goes like 1 over the coupling. In the case of toroidal compactifications, we see that the like states can be the Kaluza-Klein modes if you go to the infinite distance limit. It could be winding modes as you go to the 0 distance limit, 0 radius limit. Yeah.
question for non-string quantum gravity, if there exists that kind of thing. Your argument seems like it happens in string theory, but...
Right, so if it is a non-string theory example, then there's no reason why we would have a bunch of winding modes. So this is supposed to be a property of stringy realizations of quantum gravity. So not any low energy theory would have to respect the Swampland distance conjecture. Those that do not respect the Swampland distance conjecture would not be something that comes out from string theory.
Sorry? Can I ask a question?
Yeah.
So according to your extended object picture, if you try to compactify string or M theory on small, higher dimensional manifold without the right cycles to wrap any branes, would that lead to a immediate contradiction?
So
let's say if you try to wrap M theory, let's say on 6 sphere or something, you can't either wrap M2 or M5, so
right.
So does that mean that M theory cannot be compactified on small 6 sphere?
So here we only need light or tensionless objects. It doesn't have to have the right dimensions, right?
Yeah,
so
but on 6 sphere you cannot wrap either M2 branes or M5 branes. They all split. They don't exist cycles.
So in this case,
ruling out that compactification.
So if you cannot find any objects that would become tensionless in the limit, that would be a contradiction with this conjecture. So, but usually when you string the entire manifold to 0, this internal cycles would also string. So you have to find a limit where this does not happen for the right objects to exist.
I was just imagining a 6 sphere where there is no non-trivial cycles. So
right.
No conjecture will be ruling that out.
So, so you're asking whether you string something to 0 size. So this would be the boundary of the moduli space when you string it to 0. Whether there are some like degrees of freedom that come out. But I guess in that case, yeah. So the conjecture, as stated, is you have to find a new degrees of freedom that emerge in this limit, and if there are no degrees of freedom that becomes light in that limit, it's a contradiction with the conjecture. But you have higher dimensional branes other than 5 branes, right? So like 7 branes.
M theory?
No. Oh, okay. M theory. No.
okay, but I got your point.
Okay. All right. So let's see. Okay. So this is actually a good place to stop. So let me just summarize the lecture today. So I have introduced several Swampland conjectures and presented some light evidences for them. We will go through some of these arguments in more detail next time. And also, we have discussed some simple applications of these conjectures. Namely, in the example of no global symmetries, you can apply it to constrain models of mealy charged dark matter. And as you will see in the coming lectures, many of these statements are related in an intricate way. That's why I showed you earlier the web of conjectures. You'll see how they fit together. Now, this is my plan for the next few lectures. Tomorrow, we will go through a proof of the mild form of the weak gravity conjecture using unitarity and causality arguments. And we will also present evidence for a stronger version of the weak gravity conjecture, known as the Tower weak gravity conjecture. It's very similar in spirit to the sublattice weak gravity conjecture that we described today, except that what we can gather from looking at unitarity and causality is a weaker version. We only require infinitely many charge states to be there. They don't have to form a lattice or a sublattice at all. And in the third lectures, we will apply some of the Swampland conjectures that we described today to inflation and to particle physics. And finally, the topic for the last lecture will be de Sitter vacuum in string theory and the Swampland. So this is a good place to stop. And thank you for your attention.
So, should we see Swampland conjectures as a like constraints on the general features of quantum gravity, or constant on string theory? Because it may happen that like my like at the far UV my theory is something which is not string theory, but whose features are like some ingredients we are using to build string inspired models that are very similar to string theory.
So if I understand what you're asking, so if you look at string constructions, they seem to all satisfy the conjectures that I mentioned today, including the Swampland distance conjecture. And so you could take it as circumstantial evidence for the conjecture, and you could also, we'll provide some more evidence for the conjectures based on other arguments.
No, what I'm saying is,
suppose this is correct, suppose the conjectures can be proven, or we have enough evidence for the conjecture, you can use it as a criteria to test whether a certain way of realizing gauge theories and gravity is compatible with the conjectures.
But that may not be coming from like string theory necessarily. That may come from some other quantum theory of gravity, whose like the consistency condition that we are considering is very similar to string theory.
Yeah. So some of them supposedly would hold for other formulations of quantum gravity, although I don't know enough about other formulations to say whether they are satisfied or not. But the Swampland distance conjecture is already very suggestive of strings. The fact that when you go to different limits of the modular space, you find different states that becomes light. In particular, the examples that we study here would tell you that when you go to the small radius limits, you will get a like states, and the only way to get this like states is to have extended objects. So whether you start from string theory or not, you find extended objects in the end. So maybe such criteria for quantum gravity cannot be satisfied by other formulations. I don't know.
And when you talk about this existence of extended objects like strings or branes, so like does the conjecture say anything about the sizes of these extended objects? Because like if it is big enough, then it should be experimentally testable.
If it is.
So like when you say that like existence of some extended objects in the consistent quantum theory of gravity, do you mean only existence or existence up to above a certain critical size, like
yeah. So here the argument is only about existence, right? Because we don't know about we only know that there must be some extended objects to give us this like states. We don't actually know what they are. They could be branes rubbing around cycles or strings rubbing around cycles. We know very little, but the fact that they have to be there is suggested by the conjecture. So we don't know whether this has to be what's the dimension of the branes and whether they have to be extended along well. In this case, we know that they have to be extended along the four-dimensional space.
So like some like effective field theory of gravity should also classically have them as solution. Like some effective field theory of gravity should also have them as a classical solution, this extended object.
So you are referring to the charge p-brane solutions that was described earlier. Okay, so yeah, so that would exist in U1 gauge theory coupled to gravity. You can define the notion of extremal objects or super extremal objects already. And the weak gravity conjecture is just a statement that there must be some super extremal branes. Without that conjecture, you don't have to have such super extremal object. But the notion of extremality is already there.
Are there any other questions?
I wonder which of these conjectures is applicable to the fundamental fields, or which of these conjectures is applicable to the fundamental field or some composite effective field.
Right. So for the weak gravity conjecture, we are talking about the long-range force. So you could also have forces that don't give rise to a long-range interactions, and so the weak gravity conjecture will not apply to those cases. Right. So if you're talking about things that are mediated by a massive gauge fields, then it would fall outside the classification of the weak gravity conjecture. So maybe you can tell me what you have in mind. What are the what other theories you have in mind?
Such as some effective field in the maybe some composite Higgs, like this scalar field, does it should satisfy the conjecture constraint from Swampland?
Okay. So, for instance, if you're talking about the Swampland distance conjecture, these are the moduli fields. Yes. Right? So, for composite fields, I don't know how to even. I mean, there's no notion of the modular space to begin, even before you introduce the potential. And so I don't think we could immediately say anything about the scalar degrees of freedom that are not part of the modular space.
Is there, in higher spin gravity, is there some analogous statement like a weak gravity conjecture?
Higher spin.
Also, you can maybe people also expect that can come from the tensionless limit of the string. So
Yeah. So we would talk about an application of the weak gravity conjecture to higher dimensional branes in the third or the fourth lectures. So this is the ADS instability conjecture. So the higher spin theories would fall precisely outside of the regime of validity of that conjecture. So higher spin theories, some of them have infinitely many degrees of freedom in the low energy. And so they don't fall into the criteria that they were outside the classifications that we would consider.
okay, is there might be some analogy, or like you can maybe consider like a W3 gravity, or like you don't have to go to the infinite, but the lower dimension you maybe consider W3 gravity or W4, and there is there some like between some charge of the graviton or W3 charge or W4 charge? Yeah.
Mm-hmm.
Is there some relation?
Right. I don't know. So that might be.
Any other questions, comments, conjectures? If not, let's thank Professor Shiu again.
Thank you.